Okay, so today in class we're going to review how to draw model of matter diagrams or MoM diagrams, and then once we've reviewed that, we are going to go ahead and start doing or learning about the 5 different types of chemical reactions. So that's where we're going to start today, and that's kind of how we're going to go through things today. But let's begin by remembering how we drew model of matter diagrams in the past. So once upon a time, a long time ago, we drew model of matter diagrams, and we just drew 2 shapes bonded together when we knew it was a compound. So no matter what the compound itself was, you might have drawn something that looks like this and called it a compound. Okay. Now that we are familiar and aware of chemical formulas and what those numbers in the subscripts actually tell us, we are going to go ahead and relearn how to draw compounds to reflect the subscripts in a chemical formula. So when we draw something like a chemical formula like silver nitrate, for example, like we were working with the other day, we generally have to identify what that ratio of metal to non-metal is. There are some exceptions, sort of, kind of. So at one point, we learned how to draw Lewis structures for like polyatomic ions. When this one might look something like this, if we drew the Lewis structure for CO3, and we drew it like this. And when we did that, one of the things that we talked about was the idea that the polyatomic ion acts as one unit of something, even though it's many atoms bonded together. So when you see a polyatomic ion as part of a chemical compound, instead of drawing all of the things in terms of shapes, we're just going to give it a singular shape, like maybe a triangle. Does that make sense? So instead of drawing the carbon, the oxygen, we'll just draw a triangle to represent the polyatomic ion. Then the last thing that we need to remember is that we always connected our shapes with lines. Each line was representative of a bond. And so we'll just kind of try a couple of examples here. So in the case of the first one, CaCl2, right? One of the things we always did was when we had a lot of elements or substances around, we usually made some type of a key. So in this example, I have calcium, and I might identify calcium to be a square. And I have, chlorine. And so I might represent it as a triangle in this case. But this formula has 2 chlorines, so I need 2 triangles. So when I go to draw this structure, I always try to draw the structure so the same shapes are not next to each other. And in this case, I'm going to look for the odd numbered out shape, which in this case is the square, and place that one in the middle. So my formula, or my model of matter diagram, I guess, for CaCl2 would look something like this. So far, so good? Okay. The common mistake that students tend to make when drawing these types of structures is they will do this. They'll draw it in the order that it's written. Hold on. And they'll bond it together. And they'll be like, what? That makes sense, right? And I'll be like, no, you can't do that because we don't want to have, in this instance, the chlorine next to the chlorine. Okay. We want to have the calcium in between the chlorines, and that just kind of makes the most sense. So next example is Na3PO4. And again, I'm just going to kind of draw some structures here. So I'm going to identify that sodium, in this case, let's say sodium is a circle, and I've got 3 of them. And then I have PO4. Now, I know from my friend the periodic table, and if you don't have your periodic table out, if you don't have your friend out, you might want to get your friend out. So why don't you go ahead and get your friend out and take a look-see at your friend real quick once, and then go ahead and identify that PO4 on here, because it should be written on the back of your periodic table, is a polyatomic ion. So I'm going to write PO4, and we just discussed that the polyatomic ion is going to be 1 unit. Okay. Now, just like we did over here with CaCl2, right? I took the 1 unit and I put it in the middle. Okay. And then I attached everything else to the 1 unit. So I'm going to do the same thing here. In this case, I am going to take my PO4, put it in the middle, and I'm going to attach my sodiums around it like so, with a dot, like a dash or a dot like that. Questions? Okay. I want you to give it the old GHS try here on Ca3PO4. Ready, set. So in this example, instead of just drawing over and over and over again that there were 3, like Ca as my record keeping, I just drew Ca square, and then I said there's 3 of them, so multiply by 3. But then the next thing I did is I made the pattern of square, triangle, square, triangle, square. Okay, in an effort to just kind of show that this is 1 unit of something, 1 unit of a compound. Question so far? Excellent. Okay, so if you didn't quite get that, make sure that you have that, and then we will go and move forward. So diatomic elements, oh man, I like thinking about how words are made. So at some point, if you take a medical terminology class, you're going to learn a whole bunch of stuff. But like, I like thinking about like, what does that mean? And like, what does this part of the word mean? And like, what does this part of the word mean? And they all mean or tell you something really specific. Like, we might remember that di means 2, and we might know that atom is actually refers to atom, right? And IC in this instance really means pertaining to. So the phrase or the word diatomic actually translates to pertaining to 2 atoms. Now, the reason why that's important is because there are some elements out there that when they are by themselves, they are so unstable or reactive that they can't exist by themselves. A good example of that would be the element oxygen as a gas. Okay, you may know someone or have seen on the TV or in the movies a human being who has to use oxygen to like help them breathe. Like, the person who might have the oxygen tank that they kind of carry around with them, and they have like the oxygen mask, right? Or in the movies or in the TV, like they have the little tube that sticks like right underneath your nose there. You know what I'm talking about? What that is it's actually, in many cases, it's pure oxygen. It's just O, gas. Okay. And if it's just O, gas, the issue is oxygen is so unstable. It's not just one individual atom of oxygen. It's actually oxygen bonded to itself. So it actually is O2. And there are 7 elements that in their natural state are so unstable by themselves that when you have that pure element, it's not just 1 atom, but it's 2 atoms. So it's like H2, O2, N2, F2, Cl2, Br2, I2. Like, that's how we find these things in nature. Now, how are you supposed to remember this? You could write it on the back of your periodic table. You just could. You could write it on the front of your periodic table. You just could. Or you could remember it the way that it was taught to me when I was your age. When I was your age, my high school chemistry teacher wrote them like this. So he wrote them as Br2, I2, N2, Cl2, H2, O2, F2. And he told us that that was the name of a gentleman named Mr. Brinkelhoff. Brinkelhoff. That's how we were supposed to remember it. And we had to memorize it back in the day. And that's how we did memorize it. Now, since then, I've learned some things about the elements, and I've looked at my periodic table, and somebody else showed me this little trick-a-do here. So if you locate nitrogen on your periodic table, it's element number 7, and you locate directly to its left, you're going to see the oxygen, and directly to that's left, you're going to see a fluorine, and then directly below that, you're going to see a chlorine, and directly below that, you will see a bromine, and directly below that, you will see an iodine. If you trace with your finger starting at nitrogen and going down to iodine, what number does that make? A 7, right? So another way to look at it or remember these is hydrogen and the super 7. Saving chemistry one periodic table at a time. So like I've seen people take their highlighter and draw a 7, and then make a little asterisk-y thing instead of hydrogen, and now it's like the Avengers of chemistry, hydrogen and the super 7, or something like that. I just might get sued by Marvel for saying that out loud. Now, so you should be familiar with the diatomic elements, and the reason why they are important in this unit and going forward is every time that you write elemental hydrogen, you have to write it as H2. Every time you write elemental chlorine, you have to write it as Cl2. And if you have it somehow memorized or written on your periodic table so that you know where it is all the time, then you won't forget that, hopefully. So let's talk about the 5 different types of chemical reactions. You got your synthesis, you got your decomposition, you got your single replacement, you got your double replacement, you got your combustion. We already talked a little bit about combustion in the past, but we're going to continue moving forward, and we're going to focus a little bit more on one of them today. Ready? Here we go. Oh, I got ahead of myself. Some model of matter diagrams. Your formula should be reflective of the subscripts. We just talked about that at the beginning of this lesson. You need to use a key to indicate what each symbol represents. Make sure that's something you're able to do. And the states of matter are something that you should be able to show when drawing. So like in this instance here, solids are drawn organized and touching. Right? So when you draw a solid anything, it's going to be organized and it's going to be touching. And it should probably be at the bottom of the box or whatever you're drawing it at. Note that I drew 8 of them. Liquids are going to be touching but not organized. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. We'll do one more. Note they are also, I guess, disorganized, but they're also touching. And then your gases are going to be not touching and not organized. Something like that. And now your aqueous situation is going to be represented by being dissolved in water with an X. And so I'm going to use the circulatory system organ that's the most important, in my opinion. 2, 3, 4, 5, 6 to represent here. 1, 2, 3, 4, 5, 6, 7, 8. And then the last thing we have to do is we have to surround all of these drawings, these hearts, if you will, with water. And in our model of matter diagrams, we can represent water as an X or a series of X's like so. So far, so good? Excellent. Now, so make sure that you're doing those things. And now we're going to talk a little bit about the very, very first type of reaction, and we're going to use iron and copper chloride to help illustrate that. But in order to set that up, I need to go grab my materials. Hold on. So here I have, in this particular vessel right here, I have copper chloride. And in this particular hand right here, I have a common ordinary nail, which actually is made up of iron. Now, I'm going to do this reaction really quick once. So pay close attention. We'll come back to it. Let's talk about this for a second.
That's so cool.
You have no idea how room temperature that was. Now, so we have iron in this instance, and hopefully, so we're gonna make some observations. And we had iron, right? And we had copper chloride. Now, iron. Thinking about state of matter, color or lack thereof, texture, transparency, etc., what would you say about the iron itself? Solid? Yep, we got a solid. What else?
Silver.
Yep, we could say it's silver. One might argue it's gray. What else could you say? Think about the texture of a nail. Smooth, we'll say it's smooth for today. Somebody might say it's hard, but we can go with smooth. And I think that that's pretty good. So up here in my top reaction, I'm going to put an S behind it to tell the world that we have a solid. Now, my copper chloride, CuCl2. What state of matter would we be talking about here? Agreed. This is going to be aqueous, right? And that would indicate that what is true? That something was dissolved in water. Good. What would we say about its color? It's like a blue. It's a shade of blue. I don't want to get into an argument about what kind of blue it is. Okay. And this morning, well, I guess what would we say about, the transparency of this situation here? I don't know. It's not really transparent, although this morning it was transparent. But we're at the bottom of the barrel now, so it's less transparent. Pardon?
Like cloudy.
Yeah, we could say it's cloudy. I'll give you that. Now, since we said that this is aqueous, we're going to do that. Okay. So in the lab that you did, right, you took copper and you put copper into silver nitrate, and then all of a sudden, through the magic of either wizardry or chemistry, silver appeared out of what appeared to be nowhere, but it really came from the solution, right? Does that make sense? So this is a very, very similar reaction. So we have our iron and we have our copper chloride, and what's going to actually happen is this. Hang on, I'll bring it around. Okay, so the observations that I heard some of you say out loud as we were walking around were some great observations, and we'll address those in a second. But what I really, really want to talk about right now is the color, right? So many of you observed that there was a definite color thing going on. And so what color would you say is present?
Red.
Reddish, brownish. Both are correct, I think. And I'm going to go ish because that's the most technical term I can come up with. What would you say about the state of matter for that red-ish, brownish substance? Yeah, definitely a solid. And then I'm going to help you out here with what I think was the texture. I'm going to say it's gritty. So it wasn't quite smooth, but it was gritty. Now, before we go any further, looking at the chemical reaction, so looking at the elements that are present, Fe, Cu, and Cl, which of those elements, to your knowledge, is a color that is somewhere in the reddish brownish range? Cu, absolutely. So that was Cu that was forming on the nail. And I heard more than one person say it's like rust. And so we need to talk quickly about how it could not be rust in this instance. One thing that you may or may not know about rust itself is rust is the reaction of iron and oxygen. Okay? It's called oxidizing or oxidation. In this chemical reaction, there is no oxygen present in the chemical reaction. So this means that rust could not have formed. Going back to the law of conservation of matter, the law of conservation of matter says that what you start with, you have to end with, and you can't just make stuff up. But even though it looks a lot like rust, in this case, it definitely was not. Okay? So what does that tell me? That tells me that in this particular reaction, I'm going to produce some copper. And then what's left over? If I can't make new stuff and I can't lose stuff, what would be left over then? Fe and Cl. And I'm going to tell you that in this case, it's going to be FeCl3. And then we're going to need to try to balance this. So I know going from left to right, I've got Fe, I've got Cu, and I've got Cl. On my reactant side, I've got one Fe, one Cu, and two Cls. And on my product side, I've got one Cu, one Fe, and three Cls. So again, going from left to right, my irons, I have one on each side. Yes, ma'am?
Why is it Cl3 and not 2?
The question is, why is it Cl3 and not 2? The answer to that question has to do with the charge of the iron present. And
do you have to know that?
The question is, do you have to know what the charge of the iron is? The answer to that question is it depends. So if it's an element that you know the charge of, because of the periodic table, yes. If it's an element that you can't necessarily predict the charge of, we will give it to you. So that's why I answered with the incredibly vague, it depends. Now, going from left to right, my irons are balanced. I've got one on both sides. My coppers are balanced. I've got one on both sides. My chlorines are not. I've got a 2 and I've got a 3. I call this the odd-even dilemma. With the odd-even dilemma, what I usually do is I try to rectify the odd-even dilemma with the lowest common multiple. So what is the lowest common multiple of 2 and 3? 6, right? So I'm going to try to make sure that both chlorines end up with 6. So that means that in this instance, I'm going to throw a 3 here, which will give me 6 chlorines on my left side, but it also is going to give me 3 coppers. And I'm going to put a 2 here. It's going to give me my 6 chlorines on my right side and 2 irons. So now I need to go back and balance everything else out. My irons are 1 on the reactant side and 2 on the product side. So I need to put a coefficient of 2 here to give me my 2 irons. My coppers are 3 on the reactant side, 1 on the product side. So I need to put a coefficient of 3 here. And now everybody's happy. So far, so good. Going to keep rolling. Here we go. Oh, same reaction. Why is that frozen up there? How did that? Why? Oh no! It just. Hold on. Technical difficulties, so we could finish the lesson. All right, now here we go. So we already had balanced this particular reaction by simply saying that we had a 3 here and a 2 here, which meant we needed a 3 here and we needed a 2 here. We also identified pretty quickly early on that this was a solid, and we said that this was aqueous, and we agreed that this was a solid. So what would you guess the state of matter for the leftover Fe and Cl would probably be? Aqueous. Fantastic. Now, when we go to draw what's happening here, okay? So when we go to draw it, we have to be able to represent accurately the number of each element that is present at each spot. So there's no subscript behind the Fe, correct, in the first spot, but there is a coefficient of 2 in front of it. And that coefficient of 2 tells me that I have to represent Fe twice. So what I'm going to do is I'm going to draw Fe, and here's my key. It's going to be a box times 2. So that would look something like this. Box, box. Solids are drawn usually at the bottom of our drawing area. All right, now, next thing. I've got Cu. So I'm going to say that Cu I'm going to represent as, I don't know, a triangle. And Cl I'm going to represent as a circle. I have 2 Cl's here in the formula, so it's Cl times 2. Now, do you see how there's a 3 in front of the CuCl2? Right? So that tells me that whatever I draw, I have to draw it times 3. So that means I have to draw 3 units of CuCl2. And I'm going to do that first. So I'm going to draw my 3 units of ClCl2. So I try. Oh, that's an A. Triangle, triangle, triangle. And to the triangles, I'm going to put a couple of circles. And I'm going to bind them together with a line, like so. Now, we said that's aqueous, so what does that mean? We got to draw X's around it to indicate that water is present. So I usually just use pretty big X's to fill my space. I try to make sure that each unit is really shown to be completely surrounded by the water. A good solid, no, not solid, a good dissolving process. Okay. Now, in my product side, okay, because this is occurring in one beaker, right? Because this is occurring in one beaker, I'm going to draw it all together in the same spot. So now I've got my copper, right, which we know is a triangle because we've already identified that to be a triangle. And because there's a 3 in front, I'm going to need 3 of them. So I'm going to draw this as a solid like so. So far, so good. Now, I have iron, right? And according to this 2 in front of the FeCl3, I have iron times 2. And in my Cl3, so that's going to be a circle again. Something like, well, I guess it'll be times 6. So now I'm going to draw that, okay? So I'm going to draw those units to look something like this. So I've got a square, I've got a square, and to each square, I'm going to bind 3 chlorines with a dash. And now, because we know that this whole situation is going to be aqueous, I'm going to aqueous it by drawing a bunch of X's surrounding all of my stuff to indicate that it's been dissolved in water like so. Whee! Now, your job at some point in the very near future is going to be to identify the type of reaction that is presented to you. And you're going to have to do it by simply looking at the chemical equation given to you. So there's a couple of ways that we keep track of that. One of the ways that we keep track of that is by putting into words what that chemical reaction is. So when I say start, I mean reactants. And I would say that you have one element and one compound. So all single replacement reactions start with one element and one compound. Now, the general formula is not trickier. It's just a way to represent it. So I use letters, and the letters that I'm going to use are going to be like so. So I'm going to take B plus AY will react to form BY plus A. Now, this format is for a metal replacing a metal. Okay. So, for example, this would be a metal, this would be a metal, this would be a nonmetal. This would be a metal, and this would be a metal, but this would be a nonmetal. There's another type of single replacement reaction, and that looks something like this. And so this would be for a nonmetal replacing a nonmetal. So here I would have a nonmetal, a metal, a nonmetal, a metal, a nonmetal, and a nonmetal. And we can use these general formulas or generic templates to help predict what the products are going to be. So here we go. As an example, I see that I have aluminum, which, according to my friend in the periodic table here, is going to be a metal, right? And I see I have copper, which also is a metal. And SO4, you may recall polyatomic ion, right? So in this instance, I have a metal, and there's a metal and a metal trying to replace each other. So it's going to be a reaction that looks a little something like this. B plus AY reacts to form BY plus A. And the reason why I'm writing the general formula, like kind of right over the compound and the element itself, is because now all I'm going to do is I'm going to separate what I have and match it up on the product side, right? So if aluminum is under B on the reactant side, I'm going to put aluminum under B on the product side. So now I'm going to put my aluminum over here. And if Cu is under A on the reactant side, I'm going to put Cu under A on the product side, like that. And if SO4, which is a polyatomic ion, I'm going to give it a hug because it needs one, is under Y on the reactant side, I'm going to put it under Y on the product side. So SO4. Now, I want to leave it like that, but I can't. Because you might recall that at some point in the past, whenever you made formulas, you had to do something like checking charges and crisscrossing them down. Do you remember that? Last semester? It was in January, December of last semester. So we're going to do that now. So we're going to take our aluminum, which is a metal, and we're going to locate aluminum's charge on the periodic table, which is a +3. We're going to locate SO4, which is a polyatomic ion, and we're going to find out that its charge is a -2. We are going to crisscross the charges down to get something like Al2 SO4 3. So in our chemical formula up above, we have to have Al2 SO4 3. You got to have it. Now we can balance this thing. So I have aluminum, copper, and sulfate, SO4. On the left side, I've got 1 aluminum, 1 copper, 1 sulfate. On the right side, I've got 2 aluminums, 3 sulfates, and 1 copper. Going from left to right, I have 1 aluminum on the left side, 2 aluminums on the right side. So that means I'm going to put a coefficient of 2 here to give me my 2 aluminums. I have 1 copper on both sides, so I'm going to leave that alone for now. But I see that I have 1 sulfate on the left side and 3 sulfates on the right side. So I need to put a coefficient of 3 here to give me my 3 sulfates. But it's also going to give me 3 coppers, which means I have to go ahead and add a 3 here to give me 3 coppers. And I'm going to leave a 1 here because I don't want to leave it by itself. And so that's what you're going to have to do with chemical reactions in this unit. You are going to have to use a generic formula to identify what the products are going to look like. You have to check your charges and crisscross them down, and then you have to balance. Now, let's come back to this. Oh, it all fell off. Shoot. I was going to make a joke that, it definitely fell off. There's a lot of gunk in here, but if it stays on here, it looks like a forbidden corn dog. I'll show you when I come around. All right, but that's our lesson for today, and I'm sorry that you don't have homework. Chem is try, not chem is cry.